Hello, good evening, and welcome to the session 6 of Ellipse. In this session, we're going to see normal and its property and also the reflection property of ellipse. So let's go ahead. So normal to the ellipse. Normal to the ellipse. So what is a normal to the ellipse? So a line perpendicular to the a line perpendicular to the tangent at the point of contact. At the point of contact. So line perpendicular to a tangent at the point of contact is my normal. So with the diagram, if I have to see, then you can see this one. So this is my ellipse, and here is my point P, say x1, y1. And now this is my tangent line. The red line is my tangent line. And now this is the point here. So the line which is perpendicular to this tangent at this point of contact is my normal, denoted by n here. So let Px1, y1 be a point on the ellipse. Be a point on the ellipse. X square over a square plus y square over b square is equal to 1. So we differentiate now. So I'll be having 2x over a square is equal to minus 2y by b square dy by dx. So from here we get dy over dx is equal to this 2 and 2 we can get rid of. So I'll be having minus b square x over a square y. So this is my point P. So therefore, slope of the normal at point P. This would be the reciprocal of this. So I'll be having minus b squared. At the place of x, I'll be writing x1. So in this regard, I'll be having a square y1 over b square x1. So this is going to be my slope of normal. So therefore, equation of normal, we can have it here. So equation of normal at P would be simply y minus y1 is equal to slope we have a square y1 over b square x1 into x minus x1. So this is my equation of normal. Let's simplify this further. So we can now multiply here. So I'll be having y minus, wait, I'll just take this equation instead. So simplify now. This would give me b square y into x1 minus b square x1 y1 is equal to a square x y1 minus a square x1 y1. Now we'll collect this one and this one together. So I'll be having b square y x1 minus a square x y1 is equal to b square and then minus a square, and this would be x1 into y1. So I'll divide this by x1 y1. So this gives me we'll write down here. I'm dividing by x1 y1 throughout. So this part says goodbye, and this will give me x1 x1 cancels. So yes, b square y over y1 minus a square and then x over x1 is equal to b square minus a square. You can get this equation, or some people choose to prefer a square at the beginning. So they would write a square x over x1 minus b square y over y1, and this would give me a square minus b square. And this is the most seen form of the equation of normal at point P. Normal in parametric form. So normal in parametric form. That means what? If my P is of the form A cos theta and B sin theta in this form. So I'm going to have A square x1 would be replaced by simply A cos theta minus B square y, and y1 is B sin theta. This gives me a square minus b square. So this a and this a cancels. This b and this b cancels. So I get ax by cos theta minus by sine theta is equal to a square minus b square. So this is the equation of normal. In parametric form, this is the equation of normal at point P. Now, suppose I want the equation of normal in slope form. That means I want the equation of normal having slope m. So the equation of normal having slope m. Let's derive this. So we already have the slope of the normal. Slope of the normal is this here. So since slope of the normal is, you have a square y1 over b square x1. So a square y1 over b square x1. So this is my slope. I'll use, instead of mn, I'll simply use small m because we need to get the equation. So this is the slope of normal instead. Slope of normal. Now what I want is, I want either y1 or x1. So we can collect here. So y1 would be m b square x1 over a square is equal to y1. This is my y1 now. And now since px1 comma y1 lies on the ellipse. So my this point lies on the ellipse. Get lost, man. Or I'll be having x1 square by a square plus y1 means m b square x1 over a square the whole square. This is y1 square over b square is equal to 1. So now from this collection we can get our x1. So this gives me basically, we can simplify this further. So x1 square over a square. So x1 square over a square plus m square b power 4 x1 square over a power 4 into b square is equal to 1. So from here I get to see that this b square gets cancelled. A square roots are all yes. So from here b square gets cancelled. That means I get now x1 square over a square plus m square b square into x1 square over a to the power 4 is equal to 1. We take x1 square common, and this is a square, so I'll multiply here by a square better instead of taking common, plus m square b square x1 square by a to the power 4 is equal to 1. So from here easily we see that x1 square is going to be a to the power 4 over a square, it's not a1, a square. So this is going to be a square plus m square b square. Now from here we get our x1 is equal to plus or minus a square upon a square plus m square b square plus m square b square. So this is my x1. Now since y1 is equal to, y1 we had found was m b square a square. So m b square by a square into x1. That is I can plug in here. So I get y1 is equal to m b square by a square into x1 is plus minus a square by a square plus m square b square. This cancels b square, so I get y1 is equal to plus or minus m b square by a square plus m square b square. So a square plus m square b square. This is my point y1. So since both of them have same sign, so therefore we can get the equation of normal. So we get the equation of normal. We get the equation of normal from here. So we already have x1, y1, we also have the slope. Bracket y minus y1 is mb square by a square, this a square, a square plus mb square is equal to m into x minus x1 is a square over a square plus m square b square. So this implies I get y is equal to, this will be mx, and this guy I'll transfer to this side, so I'll be having plus of m common, then we get b square minus a square over a square plus m square into b square. So this is the equation of normal. If you take this one, or even if you can add on plus minus. So there are two choices. So y is equal to mx plus or minus m times b square minus a square over a square plus m square b square. So also this is the condition for a line y equal to mx plus c being a normal. We can utilize this condition as well. So this is all about the equation of normal. Now let's go and see the properties of normal one by one. Yeah. And this one small error here. This everywhere it is since it is x square, so I need to add the square root here. So this becomes the square root. So each part here is a square root basically. And here also. This is the equation for normal. And now if we want the line y equal to mx plus c be a normal to the ellipse, then the condition would be what? Y equal to mx plus c. So this would be the condition. That means I want my c to be what? So m square, b square minus a square, the whole square, and this square will be squared. Okay, so this is the equation for normal, and this is the condition for this line to be normal to these ellipse. Now we'll see the properties of normal. Let's note down. So properties of normal. So in the first property, if a normal at point P on the ellipse cuts the major axis at Q and minor axis at R, then PQ is to PR is P square over A square. So for this ellipse, we have assumed that A is more than B, as if this is standard. So since the major axis, it cuts at Q. Major axis, it cuts at Q. So major axis would be here, and this point Q, and this is the minor axis, which is at R. This is my normal. And here I have the point P. So we have to show that PQ over PR, because we have to show that PQ over PR. We need to find out this. We have to show that it's B square over A square. So let's go ahead. So we'll do one thing. We have this point here, say x1, y1. So we know the equation of normal. So the equation of normal at P. So equation of normal at P, no, we already have the equation here. This is the equation of normal. Yes. This is the equation of normal. So I'll be having here a square x over x1. So I'll just simply select this instead of writing. My equation of normal happens. This normal leads the major axis at Q. So we want to know the coordinates of Q. So at Q, what happens? Y is 0. So when y is 0, that means this entire thing is gone. So I'll be having my x point. So x would be simply a square minus b square over x1 upon a square. So coordinates of Q are basically, we can simplify this, and I can write down here 1 minus b square over a square times x1 comma 0. And add r, what happens? My x is 0. So when x is 0, this gets cancelled, and I'll be having here y is equal to uh, b square minus a square into y1 over b square. So coordinates of r are basically it's 0, comma. We can simplify this here again, and I'll be having 1 minus a square over b square times y1. This is my r. Now we need here PQ over PR, so this is going to be distance formula. Rather, what we do, we find out PQ square over PR square. So PQ square over PR square, I'll find out, so that I have to use the distance formula. So in the distance formula, I'll be having X, Q is here. So when I do PQ, I'll be writing here X1 minus this. So this coordinate can be even written further like this. This one can be replaced by X1. That means we have multiplied here X1 basically, and here I'll be multiplying Y1. So that means now I can now write down Y1 square, and this will be Y1 minus Y1. Like this, we have multiplied here. So now it makes our task easy. So since we want PQ square, so PQ square would be simply what? This distance, this point minus this. So X1 gets cancelled, and I get only minus P square over A square into X1 square plus y1 square. This is my PQ square. And when I find out PR square, so PR square is also almost same, because here now I get just simply x1 square plus y1 minus this, so y1 cancels, and we get a square y1 over b square, the whole square. So this is what my PQ square and PR square is. Now we just want their ratio, so we'll directly just take the ratio. I'll remove this, I no longer need them. So I'll now simply take the ratio. So this gives me PQ square over PR square would be equal to, we can multiply this further, and this gives me b power 4 x1 square plus a square into y1 square, the whole upon this a square will be multiplied in the denominator also, and this gives me x1 square times b power 4 plus this would give me a power 4 into y1 square, and this I can multiply b square in the numerator there, yes. So if we see here that this is b4, this would be a power 4 basically. This, when I open this, this is b power 4 into x square, this is a power 4, so I get here a power 4 instead. And here also this becomes a power 4, and this would be b power 4. So that this b power 4 x1 square plus a power 4 y1 square directly gets cancelled. So I'm now left with PQ square over PR square is equal to b power 4 over a to the power 4. So I want PQ over PR. So PQ over PR would be b square by a square. This is very important in determining the eccentricity of the ellipse. So if we have the normal here, and this meets the major axis at Q and minor axis at R, so PQ over PR would also give me eccentricity, because we know E square is equal to 1 minus B square over A square. So which means B square over A square could be written as 1 minus E square. So that means from here we get to see that PQ over PR is equal to simply 1 minus E square. So this is the another version of this property. Okay, quite useful one. Let's go for the next. We have the maximum distance of any normal to the ellipse from the center is mod of a minus b. So that means what? If we have any normal, okay, then the maximum distance from the center is going to be what? So imagine the equation of normal. The equation of normal Now, since we want this thing in the form of let's see, maximum distance of any normal, better. It will be better if you use the parametric coordinates. So the equation of normal at any point P on the ellipse, at any point P, A cos theta comma B sin theta on the ellipse is, we already have the normal, which we have derived here, AX by sec theta. What is that? Okay, AX by cos theta basically minus BY by sin theta. So AX by cos theta minus BY by sin theta is equal to A square minus B square. This is the equation of normal, which we have derived. AX by cos theta minus BY sin theta is equal to A square minus B square. So now we want the maximum distance of any normal to the ellipse from the center. So from the center means this is my line, or you say normal here, and this is the center here, which is 0, comma 0. So its distance means, of course, we want this distance. So distance are denoted by d, and this would be what? I'll be plugging here 0, 0, and this would give me a square minus b square simply over the square root of. So this would give me a square, cos square is nothing but here sec square theta plus b square sin square theta is nothing but here cosec square theta and the reciprocal. So we get this. Now we want the maximum distance. So for the maximum distance, my denominator should be minimum. So for max distance d, denominator should be maximum. Upside minimum, because we want denominator d to be maximum. So denominator should be minimum. So let's consider this thing then. So we have a square secant square theta plus b square cosec square theta. So we can write here a square sec square theta as 1 plus tan square. So 1 plus tan square theta plus b square into 1 plus cot square theta. This would give me a square plus b square plus a square tan square theta plus b square cot square theta. Now, keeping these two intact, we can apply here AMGM inequality for these two quantities. So I'll be having here, this will be greater than or equal to simply 2AB, because we can apply AMGM. So a square tan square theta plus b square cot square theta over 2 is going to be greater than or equal to the square root of their product, which is a square tan square and b square cot square. So we get 2AB. So now this is nothing but a plus b the whole square. That means I get the minimum value of denominator. So since the denominator here is in the square root, so we'll take the square root here also. So I get here a plus b. So I can plug in here. So this gives me d is equal to, so therefore d is equal to modulus of a square minus b square over a plus b as d max. So therefore d max would be equal to, we can open this and I get a minus b into a plus b over a plus b. So now politely we can get this cancelled and we get the maximum distance to be mod of a minus b. And then now we can go for the next one. Another very classic property, okay, that normal other than the axis of ellipse cannot pass through any of its foci. That means if I have an ellipse here, okay, why I have said here the normal other than axis of ellipse, because if I have an ellipse, okay, and say if I draw the tangent at the end point of the major axis here, then this is the only normal which will pass through the focus of the ellipse, Now, I have to show that there is no normal which pass through the ellipse. So I have to prove that there is no normal which pass through the focus of the ellipse, whether this one or this one, it does not matter. So now consider the equation of normal. So consider the equation of normal at any point. So consider the equation of normal at any point P. At any point P. So A cos theta, comma B sin theta. So if I have this thing, then what's the equation of normal, by the way? We have here ax by cos theta. So ax by cos theta minus by sin theta is equal to a square minus b square. Now, suppose this passes through the ellipse focus. Suppose this normal passes through the focus. Passes through the focus, say a comma 0. Then at the place of x, I'll be writing here ae, and I get here cos theta. And this guy would be 0 is equal to a square minus b square, could be written as a square e square. So from here, we get to see that this a square cancels, and this e also gets cancelled. That means we are saying 1 over e is equal to cos theta. So 1 over e is equal to cos theta. And now we know for an ellipse what happens. So for an ellipse, my e belongs to 0 to 1. That means 1 over e, okay, would belong to 1 to infinity, which means we are saying that cos theta belongs to 1 to infinity, which is a contradiction. This contradiction arises because we assume that the normal passes with the focus a comma 0. So that means our assumption is wrong. Means our assumption is wrong. So our assumption is wrong. This implies what? No normal can pass through the no normal can pass through the focus of ellipse. All right. Now let's see the reflection property of ellipse. So the another important part of this normal is the reflection property of ellipse. So here normal is the hero. That means normal here bisects the angle SP S dash. What is SP S dash? So this is my point P here, whereas the normal is being drawn. And say this is the focus S, and this is the other focus, the S dash. So we now have to prove the classic result that these two angles are equal. That means this normal is actually bisecting this angle SP S dash. Okay, so I have this point, say here N. That means I have to prove that angle S P N is same as angle S dash P N. So these two angles are equal. Okay, that means normally acting as the angle bisector. So we need to prove that. So this result you must have been following from the class 10. The angle bisector theorem. So if this line is serving as the angle bisector, so it is enough to prove that this SP over S dash P is same as SN over S dash N. So if you prove this, so this implies this line N, okay, this line is acting as the angle bisector. So that is PN is the angle bisector. So this is what we need to prove. Now let's go ahead. So again, we'll go by the very basic definition. So SP is nothing but the focal distance of the point. So SP is equal to what? EPM. So this we know already. So E times what is PM, by the way? This is perpendicular distance here, PM. So of course, my point P to be, I'll take here X1 comma Y1. So P point would be simply, if I draw the perpendicular, then PM would be, this is M1. So this point is X1 and this is A over E. So if I want to find out PM, so from A over E, I'll subtract X1. So A over E, I'll subtract X1. So this will give me simply A minus E into X1. This is SP, and S dash P would be simply E times PM dash. That means I need this point basically here. So this would give me PM dash would give me E into, so I'll add, this time I have to add X1 to it because this is A over E and this is X1 being added. So A plus E into X1. So that means we have found SP over S dash P. So SP over S dash P is simply A minus E into X1 over A plus E into X1. I'll call this result 1. Now we will go for Sn and S dash N. So let's go ahead. Oh, this is S here. And this is S dash. So we'll just join this. We have to prove that these two are the bisector. This is N. And here I have my point P. Now let's write down the equation of normal at P. So equation of normal at P. X1, Y1. So we know the equation of normal. We'll not prove this using the parametric forms. Rather, we'll use the standard one. Okay. This point form basically. So this one, a square x over x1. This one we will use. So a square x over x1 minus b square y over y1 is equal to a square minus b square. Now this normal meets the major axis at n. So at n, what happens? Y is 0. So at n, when y is 0, I get my a square x over x1 is equal to this a square minus b square can be further written as a square into b square. From the very basic result, e square is equal to b square 1 minus b square over a square. Now this a square and a square would get rid of, and I get x is equal to x1 times b square. So we know the coordinates of n now. So therefore, coordinates of n are x1 comma x1 e square comma 0. So now I can find out Sn. So Sn would be simply what? This point I know. So Sn is S is a comma 0, n is x1 e square comma 0. So I want Sn. So Sn could be written as OS minus ON. This would be Sn because OS minus ON if I do. So what is OS by the way? OS is AE minus ON is x1 into e square. So from here, if I take e common, I get a minus e into x1. I know this a minus e into x1 is someone here. So a minus e x1 is nothing but sp. So I get here e into sp we can get. And I'll find out s dash n. So s dash of n would be s dash of n. This would be os dash plus on. So os dash would be a distance only, and on is this distance is x e a square. So I'll take here e common, and this gives me a plus e into x1. So we end up proving e into s dash p. So we have proved Sn is equal to e into sp dash sp, and Sn dash s dash n is equal to e into s dash p. Yes, e into s dash p. So that means from here we get to see that sp over s dash p is equal to e gets cancelled. So we have proved that sp over s dash p is equal to Sn over s dash n, which proves that the normal is bisecting the angle. So the normal is bisecting the angle sp s dash. So we now want to derive the conclusion for this, the reflection property here. So let's write in the all possible conclusions for this. So we will now see the important findings here. So that means if this is my normal, which is acting as the angle bisector for the angle SPS dash, which means that if I consider this an incident ray, okay, which is incident from one of the focus. So if I have an incident ray which is passing through one of the focus, it will get reflected from the focus and reflected from the ellipse and will pass through the another focus. So if I have an incident ray which is passing through one of the focus, then it will get reflected from the ellipse and pass through the other focus. Now what will happen? So as this is being done, now the important finding would be, so if I just extend this line further here, like this, and this line also, if I extend it here further, then I see that this normal and the tangent, they are acting as the angle bisector for the incident ray and the reflected ray. Since the tangent and normal are perpendicular, So what happens basically? The reflection property of an ellipse we will now specify that an incident ray passing through one of the foci of the ellipse gets reflected from the ellipse and passes through the other foci. Good. And the most important point here is going to be the tangent and normal are the angle bisectors for the incident ray and reflected ray of the ellipse. And if these are the angle bisectors here, then I can prove that the image of this focus, if I take this upon any tangent, it will lie on the line SP here, like this. So this is going to be the image of my focus. Because this if I take the image of this focus in this tangent, it will lie on the line SP S dash P. So we'll now write on the finding for the for this topic. So this would be an incident reflection property would be the reflection property of ellipse. It would be an incident ray passing through one of the foci of the ellipse. One of the foci of ellipse gets reflected from the ellipse and passes through the other foci. It is equivalent to saying that the tangent and normal are the angle bisectors of incident ray and the reflected ray. Incident ray and the reflected ray. And the reflected ray. The image of focus in any tangent would lie on the reflected ray. So this would be a bold statement to make here. So for this needs an explanation here. That means if I take the image here of this focus in this tangent, so it will lie on the reflected ray, which means I should join this point and then connect it to the this interior point of this ellipse here, P, and then this would get reflected here. So I know my image would lie on this reflected line. This is what I mean by this. Okay, so that's all for the session today. We'll see you again with some more problems and some other properties of ellipse. Thank you so much. Happy learning.